Alright, one more video for this week's class, and this is going to be on using inverses to solve systems of equations. Next week we're going to explore some of the properties of the inverses. We're going to get into some details there on some theorems and other things that we can say about the inverse, and we're gonna actually develop some results, some of which are actually kind of nice results. We'll get into some of the details there. But one more sort of computational topic before we get into that, which is using inverses to solve systems. And this is, it's a result which I guess is more theoretically useful than computationally useful, even though this is a sort of a computational topic, because this is not a very efficient method, right? So the idea here is that if I have my equation a times x equals b, right, then, well, as we see here, there's a couple of ways to do this, right? I can say, well, x is equal to the identity times x, right? And the identity is a inverse times a times x. Using associativity, we get to here. And then a times x, well, that was assumed to be equal to b, right? So we get a inverse times b. That's the calculation that you see there, right? The other way to think about this is that if you start with the equation a times x equals b, right? Well, let me move the b over a little bit. So if I have a times x is equal to b, think about this like if you were solving something like 3x equals 4, right? How would you solve for x? You would multiply both sides of this equation by 1 over 3, and you would end up with x equals 4/3. So you want to do kind of the analogous thing with matrices, which would be that you multiply, so 1 over 3 is the inverse of 3 as far as multiplication of real numbers, so you'd multiply, same kind of thing, multiply both sides by the inverse. One thing you got to be careful about is that notice that it's on the left, on both sides of this equation, right? The order of matrix multiplication matters, so you can't multiply one side on the left and the other side on the right. That's not a valid operation. But if you do the same thing to the left-hand side of both, a inverse on the left, a inverse on the left, right, then on the left-hand side, the a inverse and the a, they cancel out, and they just leave you with x. And on the right-hand side, you've got a inverse times b, and so you've solved for x. This is the idea. And this method is sort of attractive because it resembles what you're used to working with numbers, but practically it's not useful because we already had one method of solving a system of equations, which is to set up an augmented matrix and do row operations. And if you think about solving that system, what would you do? You would do row operations to try and reduce the matrix A down to reduced row echelon form. How would you compute the inverse? You would do row operations to reduce the matrix A down to reduced row echelon form. And in the first case, you're dealing with a single column, right, given by B. You're dealing with a single column on the right. In computing the inverse, you have several columns on the right. So computing the inverse is more work than solving this system of equations using the methods we already had. And once you have the inverse, you still have to go out and calculate A inverse times B before you get your answer, right? So in practice, this is maybe not the best method because it takes more work. Nonetheless, there are some places where this is useful. So let's do one example where we see how we could make this work, okay? So here's a system of 3 equations and 3 unknowns. One other, I guess, area where this method fails is it's only going to work when we have the same number of variables as we have equations, right? Because we need the coefficient matrix to be square. So what is our coefficient matrix in this case? Well, we read off, okay, the x coefficients are 2, 1, minus 1. The y coefficients are minus 1, 2, 3. The z coefficients are 4, minus 2, 2, right? and we see if we can find the inverse. Also keep in mind that if A turns out to not be invertible, right, it might be that there's no solution or there are infinitely many solutions. If it's one of those two scenarios is the case, then this method also is going to fail, right? And the previous method is the one we want. I probably can't emphasize this enough, that despite the fact that we kind of go over this method as an application of the inverse, it's honestly it's a terrible method and you shouldn't do it. But let's do it anyway, just to see how it would work. Okay, so we set up our augmented matrix with A on the left, identity on the right. So we get 2 minus 1, 4, 1, 2, minus 2, minus 1, 3, 2, 1, 0, 0, 0, 1, 0, 0, 0, 1. First thing we got to do, get our leading 1. We can see that there is already a 1 hanging out in the second column. So the easiest way to get, sorry, leading 1 in the first column, second row. The easiest way to get a leading 1 here is to swap rows 1 and 2. 1, 2, minus 2, 2, minus 1, 4, right? But be careful, what you do on the left you must also do on the right. So the rest of row 2 is 0, 1, 0. The rest of row 1, 0, 0, 1, 0, 0. So we get those guys down. Row 3 stayed put. Right? Make sure you don't just do this on the left, you got to do it on the right as well. That's one place where people tend to go wrong. They forget the right hand side. Alright, now that I've got my leading 1, I want to use it to make zeros, so we're going to do row 2 minus 2 row 1. That's going to be my new row 2. Row 3 plus row 1 will be my new row 3. 1, 2, minus 2, 0, 1, 0. So I'm going to get 0. Minus 1 minus 4, I get minus 5. 4 plus 4, I get 8. 1 minus 2, 0. And now we do row 3 plus row 1. So 0, 5, 0, and then 0, 1, 1. Okay. So where do we go from here? Well, we should probably create a leading 1 in the second column, but maybe we see that there's a cheap way to create a 0 right away. So let's do that first, and then we'll do some cleanup. I'm going to do row 2 plus row 3, and make that my new row 2. Now I'm deviating a little bit from the standard algorithm here, but I'm doing it to save myself a bit of work. Right. Once you do enough of these, you can spot the occasional shortcut. So if adding row 3 to row 2, 0, so I get 0, 8, 1, minus 2 plus 1, minus 1, 1, 0, 5, 0, and then 0, 1, 1. Okay. Now I've got to create some 1s. I'm going to do 1 over 8 row 2, that's going to be my new row 2. I'm going to do 1 over 5 row 3 and make that my new row 3. 1, 2, minus 2, 1, 0, 0, 0, 1, 1 over 8 minus 1 over 8, 1 over 8, 0, 1, 0, 0, 1 over 5, 1 over 5. By the way, if you were trying to solve the system, you would probably be done by now. Let me see if I can copy this, because we're going to need another page. Okay, so I'm going to see if I can, I haven't tried this before, but let's see if it works. Okay, so we're going to create a new page. I'm going to add one page. There we go. And let's see if I can, oh, I want to take this second guy. Can I move this to another page? Oh, that's a rotate. That's a stretch. Can I move it to a new page? I can't. Okay. Alright, so we're just going to have to try and remember things here. 1, 2, minus 2. Unless I have an option. No, the limitations of the pen. Okay. Okay. Oh, interesting. My pen has stopped responding. Well, the pen hasn't stopped. The program has stopped responding. All right. I think what we're going to have to do is we're going to have to leave it here because, well, let me pause and see if I can salvage my program. Okay, so program crashed. I got it back up and running. Copied out my matrix just to move us forward. So here's where we were so far. So what do we do from here? Well, let's swap rows 2 and 3 just to get everything in the right spot. Okay, 1, 2, minus 2, 0, 1, 0, 0, 1, 0, 0, 1 over 5, 1 over 5, 0, 0, 1, 1 over 8, minus 1 over 8, 1 over 8. All right, so we're in row echelon form now, but we don't stop here because we got to get down to reduced row echelon form. So we've got to keep going. What do we do from here? We got to do our backward steps, right? So we've got to use the leading one in the third column, third row, third column to get rid of the minus 2. We got to use this leading one in the second column to get rid of the 2. So we've got to do row 1 minus 2 row 2. That's going to be my new row 1. And I've got to do these one at a time here because I've got to deal with the arithmetic over there on the right hand side, right? So let's do that one first. I guess technically I should do the other one first, but it's not really going to matter here. So let's do it. Okay, so 1, 0, minus 2. Okay, so 0 minus 0, 1 minus 2 over 5 gives me 3 over 5. 0 minus 2 over 5 gives me minus 2 over 5. And then there, 1 over 8 minus 1 over 8, 1 over 8. Okay, and finally I can do row 1 plus 2 row 3 and make that my new row 1. 1, 0, 0. There's that 0 I want. 0 plus 1 quarter, 1 quarter. 3 over 5 plus a quarter. Well, that's kind of annoying, right? 3 over 5 plus 1 over 4. Sorry, minus 1 over 4 because I got a minus sign there. Let's fix that. Okay. Common denominator is going to be 20. 12 over 20 minus 5 over 20. Okay, so 7 over 20. Similarly, I've got to do minus 2 over 5 plus a quarter. So minus 8 over 20 plus 5 over 20 minus 3 over 20. 0. 0, 1 over 5, 1 over 5, 1, 1 over 8, minus 1 over 8, 1 over 8. So we've got the identity over here, which tells me that this should be the inverse. So if that is the inverse, now I compute A inverse times, what were my numbers on the right hand side? 2, 7, minus 13. 2, 7, minus 13, and that should give me x, y, z, assuming that I didn't make any mistakes computing the inverse, which is quite likely. You still have to multiply that out. So hopefully this example is sufficiently convincing that this is maybe not the best technique to use, right? Because we could have tried solving this system using Gaussian elimination, and we probably would have been done a long time ago. Nonetheless, we'll see that there are some places where knowing that this method works will let us answer certain questions. Okay, that's it for today.